Yes, thank you. Like I was saying, this is one of my published work that I did towards or at the end of my PhD. So I was focusing on metamorphic petrology, and after getting the metamorphic condition, we're also looking at the age or the timing of metamorphism. So, but in this case, we decided to look at the age, geochronological age, at studying the detrital zircon. So we did that across the central zone of the Limpopo Complex, the Bridge Complex in both South Africa and Zimbabwe. Then we went on to the central zone in Botswana, which is the Pique Complex, as well as the Mototsa Complex. So, sorry. So the Mototsa Complex, some people, they consider it as an extension of the central zone of the Limpopo Complex. Some, they consider it as a block on its own. But from our studies of metamorphic petrology, we considered the Mototsa Complex as an extension of the south central zone of the Limpopo Complex, specifically the southern part of the Mototsa Complex. So this is the paper that we published from the Journal of African Earth Science, looking at the detrital zircon across the central zone. And where is the central zone? Central zone is found in the southern part of the African continent, within the Kalahari Craton, or it used to be Azania Craton. Then this is found in between the Kaval Craton and the Zimbabwe Craton, and this is how it looks like. This is the southern marginal zone, the northern marginal zone of the Limpopo, as well as the central zone. So our studies was focusing only on the central portion. That is the central zone Bridge in South Africa and Zimbabwe, then the Pique Complex in the Botswana side, and as well as the Mototsa Complex. So this study, so we report systematic uranium leg geochronological study of features that are obtained from the central zone of the Limpopo Complex, that is from Bridge, Pique Complex, Mototsa Complex, exposed in 3 countries, that is Zimbabwe, South Africa, and Botswana. And we analyzed or we sampled 11 quartzites. You can see the spots here, the Zimbabwe side, we have 3, we have 3 also from South African side, we have 1 from the Pique, and more from the Mototsa Complex. And from those 11 quartzites, we analyzed 765 samples. So, why did we do that? We did that so that we can find out the depositional age of those zircon. And then the provenance, where they come from, where they were derived from. And then also, we looked at the effects of high-grade metamorphism in zircon grains, especially in a polymetamorphic terrain, where metamorphism occurs more than once. And then the age has also been used to resolve the 2 contrasting tectonic models for the evolution of the Limpopo complex, that is the Limpopo Complex, which occurs between Zimbabwe and Kaval Craton, and which is considered as a collision between the 2 cratons, or some people they consider it as a cratonic origin. So these are the 2 contrasting 2 tectonic models that are existing from this Limpopo complex of the central. But there are studies that have been conducted. We have people who consider this that the Limpopo complex is the peak high-grade metamorphism of the Limpopo took place at 2.6, 2.7, and later on followed by a thermal event that took place at 2 billion, affecting the entire central zone and the shear zones, such as the triangle, the Tuli, Sadi, and the Palala shear zone. There are also those who believe that in a single collisional model, which involves Zimbabwe craton and the Kaval craton during the Neo-Archean. Then we have those who believe that, or who came up with multiple collisional model that at early stage, it was the central zone colliding with the Kaval craton at 2.68, then followed by a unified central zone and Kaval craton colliding with the Zimbabwe craton at 2.58. Then further later on, followed by this 2.0 billion intracontinental shearing. So these are some of the studies, and also there are those who believe that this Limpopo complex did not collide at Neo-Archean. They are saying the two blocks, the Zimbabwe craton and the Kaval craton, they were not at proximal. Therefore, they cannot be collision. So they suggest possibly that the collision took place at 2B, that is Rajesh 2014B. And we have also those who proposed the intracratonic recently, intracratonic granular diapia model through initial exhibition of the central zone. So now, with all these models, it shows us that the evolutionary history of the Limpopo complex continues to be a subject of active debate and controversy. And with that, we can see that there are only two metamorphic events that are recorded. Some and there is something that happened as well at geochronological. So these are the two metamorphics. So now, let's look at what our results will give. Like I was saying, we started with this quartzite. The top ones are from the Zimbabwean side. And then we have these ones from the central zone from LW5 up to C5O2E. Then we have one from the Limpopo Complex, and then these ones from the Limpopo Complex. And these are the spots where we sampled our land. They are quite rich. They are quite rich and muscovite here, and they are very massive and foliated, as you can see from the images here. So they are highly deformed. And you look at it, the photography, you can see that there's a lot of quartz. It contains a lot of quartz. Then we have muscovites, biotite, and zircons. And 90 to 99% of quartzite with the accessory minerals such as muscovite and zircon. And these quartz, they are very coarse grained, xenoplastic, polygonal, and shows irregular grain margins. And those grain boundaries are strongly irregular, showing mosaic texture, probably formed by high temperature recrystallization. So you can see these quartz, biotite, muscovite, and so on. So, but when it comes to the zircons are subdued, rounded, mostly included in quartz, and some are in the grain boundaries, typically considered as a heterogeneous. And we looking at this, can say the protolith could be the quartz-rich sandstone because they are 90% quartz-rich. Now, before we go into the interpretation of the results, we made a statement. We made a statement that the concordant ages of the detrital zircon grain with magmatic zoning, high thorium ratio of greater than 0.1 do not necessarily reflect the age of magmatic zircon crystallization, but can also be the result of partial or complete land loss caused by subsequent thermal events, such as metamorphism. Therefore, careful consideration such as core ring texture, distribution of concordant discordant data, thorium ratio should be given during analysis and interpretation of concordant. So that is what we are going to look at. We're going to look at the ring core structure, the distribution of the concordant, discordant data, the thorium ratio, and then we come up with this interpretation that we are looking to gain. So, but our results showed that all the detrital zircon ages greater than 3.1 billion are regarded as original crystallization age, with thorium greater than 0.1, and they have very little. So anything above or equivalent to 3.1 billion, we consider it as an original crystallization of those zircon grades. Anything less than that, we consider it as lead loss, as long as recorded in the as magmatic zircon. Let's see what we mean. We start with the central zone from this bubble carton. You can see that there are our zircons oscillatory zoned, irregular concentric, and we have those structureless around the core rings. But in this case here, we could not analyze because the rings were very big, so we could not analyze. But we were looking at the data with a discordant less than 10, and we consider that as a component. So now, the sports ages with oscillatory zoned core and with a ratio of 0.19 to 1.50 was suggested as magmatic origin. And in this sample, we see them ranging from 3.5 to 3.1 billion. And we consider anything that is above 3.1 as age of crystallization. And in this sample, we did not record metamorphic age. And if you can check from this diagram, you can see that the thorium uranium is more than 0.1. And if you look at the pattern of discordant and concordant data, you can see that the red one, which are less than 10% discordant, the record age is above 3 billion. And we have the discordant one, which we believe have been affected by lead loss, forming a trend which moves towards up to the Pan-African origin. And in this case, we did not get any metamorphic age. So anything above 3.1, we consider as age of crystallization. Anything less than 3.1 and it's concordant, consider it as a lead loss. Then we also move to another sample in the central zone of Zimbabwe. We also see the same thing, and we saw age of 3.5 to 3.05. And we see these ratios of 0.22 to 1.11 suggesting magmatic origin and given these ages. And whatever is above 3.1 is crystallization age. Anything less, we consider it as a lead loss. And also, if you look at the trend, you can see that they are moving from up there above 3.1 or 3.2 here in this case, and they've been pulled towards even maybe 1 billion activity or to Pan-African activity, meaning that those zircons, they are originally aged somewhere above 3.1. So due to they will head towards that metamorphic activity. If it's Pan-African origin, then they will be pulled towards the Pan-African origin. If it's 2 billion activity, they will be pulled towards 2 billion activity. Those with the lead loss, they will go along the concordant line. And those ones we consider them as lead loss as well. Then the same thing happened, but in this case here we recorded a metamorphic age. And the metamorphic age we recorded is 2 billion. So we got metamorphic age, and anything above 3.1 we consider it as an original crystallization, and then anything less we consider it as a lead loss. But in this case, we recorded metamorphic age with a thorium uranium of 0.04, and that is the one that we recorded. So the 2 billion has been recorded. Then we had another sample from the South African side. That one recorded metamorphism at 2.6 and then at 2 billion. And you can see the thorium uranium content is very less than 0.1. And you see the trend as well. You see the concordant, discordant, less than 10, they are somewhere up there. So meaning that originally this they were derived from the older ages. So due to lead loss, then they were pulled. And most of them, they are pulling towards the Pan-African activity. Because in the region, that is in like elastic metamorphic activity that affected the entire region. So that's why most of them, they pull towards this activity. So even those that were pulled towards 2 billion, they ended up being pulled towards the Pan-African activity. So then we also have same thing from the central zone. You can see they are pulling towards, and anything above 3.1 is lead loss. So all these ages that you see in between here, showing magmatic zircon, and we consider them as lead loss, So anything less than 3.1 is lead loss. So the same thing was interpreted from the Limpopo Complex, but the Limpopo Complex recorded an old grain of 3.8. So it's here. And then we also have an older grain here. So if you look at this grains here, they show that they have been pulled from up there. If you construct a line, they could be coming from up there. Meaning that still in the Limpopo Complex, the original crystallization should be greater than 3.1. Anything which is magmatic is lead loss. And here, no metamorphic age was recorded. The same thing in the Limpopo Complex. You can see they are pulling also, and we have this one, which is pulled from up there. But in this case, the oldest grain that was recorded is the 3 billion. We don't have anything greater than 3.1, but the trend of the discordant and concordant line shows that there is the crystallization of the grain could have been more than 3.1 billion. So then we also have another, you can see here, around 2.8. So it's discordant, and it shows that it could have been pulled from up there. So anything less than 3.1 is lead loss. And also no metamorphic age recorded. The same thing happened, you can see up there from our last sample from the Butodze, which recorded magmatic age of 2.6 to 2.61, but we consider it as lead loss. It's lead loss because we believe that the original crystallization is 3.1, and no metamorphic age recorded as well from this terrain. Now, in summary, we look at, to summarize this. So if you check from this diagram, you will see that most of the bed bridge complex, they dominate the age with the age of 3.1. You see a lot of them having 3.1, which is grayish. And then in the Limpopo Complex, we have this also, and we also have the oldest degree. And from the Limpopo Complex, almost all of them, they recorded younger ages less than 3.1. But those ages, we consider them as lead loss. We don't consider them as age of crystallization. Then, this quartzite from the Botswana side mostly are rejuvenated lead loss. And we suggest that it's due to diffusion processes during high-grade metamorphism. Since it's you can see from these hydration minerals, a lot of hydration minerals like muscovite and quartz. And this quartzite, they occur in the Shashe group, which consists among other rocks metabolites, which have got hydrous minerals. So maybe that could have also led to a high lead loss from those samples. Right. So now let's go to the provenance, the depositional age. Now we say our original crystallization age is 3.1. So now let's see the depositional age. The depositional age of the quartzite from the central zone were in fact based on the age of the youngest near concordant detrital grain, which is 3.1, and the oldest metamorphic age, which we recorded as 2.61. But also, there are other metamorphic ages that were recorded, like in the previous slide. This suggests that the metamorphic and tectonic activities of the Limpopo took place at 2.70 to 2.65, and as the timing of collision of the Zimbabwe craton and the Kaval craton. But the new zircon ages, quartzite belonging to the bed bridge, Butodze, and the Limpopo Complex suggest the detrital age older than 3.1 or equivalent to 3.1. And depositional age, therefore, it should be between 3.1 and 2.6, meaning that from the bed bridge, and then from the Limpopo Complex, we consider it as from the 3.2 to 2.65. This 2.65 comes from the reported age of collision between the Limpopo Complex and the Zimbabwe craton, which is 2.65. I think it was reported by the McCourt in 2004. They recorded, I think, the collision of the Limpopo Complex and the Zimbabwe craton. So, and also from the Limpopo side, also we consider those ages as metamorphic ages 2.65. So now, these results indicate that anything less than or near the results of this study indicate that less than 3.1 billion year concordant ages, the one from the magmatic crystallization character are related to lead loss due to multiple metamorphic events in those areas. So now, the provenance. Our depositional age, we consider it between 3.1 and 2.61 or 2.6. So the provenance, some people, they started to teach zircon as well from the central zone. Like there it up, he started to treat zircon from quartzite. He got ages ranging between 3.35 and 3.15. But he considered ages between 3.35 to 3.1 as related or were correlated to the local St. River Nile. So he thought these ages were derived from the St. River Nile. Looking at the similarity in terms of uranium lead, ruthenium hafnium isotope data set. Also there, consider that the digital grain older than 3.5 from his study were correlated with the Zimbabwe craton, especially the southern part. So the Caval craton lacks older rocks such as greater than 3.5, therefore it was not considered as the source of the digital zircon from the central zone. So we ignored the Caval craton. Also, Kruna also studied the metapelites, and he reported ages ranging from 3.71 to 3.36. And he suggested digital zircon from the metapelites, and those from the quartzite southern, and those of the quartzite from the Zimbabwean side are derived from the same source. So he also correlated those from the Zimbabwean plateau. In our study, we also did some correlation. We took some orthonized granutrates from the Zimbabwe plateau, and then we correlated with our results. So from our greater than 3.1 along this line, you can see that they correlate very well with the orthonized granutrates of the Toka segment from the southern part of the Zimbabwe plateau. So anything less than 3.1, we consider it as lead loss. So our age correlates very well with orthonizes from the Toka segment. And then we also correlated with the digital zircon from the same Zimbabwe plateau. And you can see that our age, which are greater than 3.1, they correlate very well, same with the quartzite from the southern part of the Zimbabwe country. So in this case, our results are very consistent with what Kruna et al. 1998 reported from as the source of the provenance of this digital zircon. So now it tells us that the Paleo-Archean, Meso-Archean digital ages discussed are nearly comparable with zircon from the Zimbabwe plateau, and particularly with the age pattern basement of the rock of the orthonized granutrates from the Toka segment. You can see from the diagrams here. And therefore, the protolith of the segments from the digital zircon of the central zone of the Limpopo complex considered to be derived from the similar Paleo to Meso-Archean magmatic suit of the Toka segment. That is the source of our digital zircon, based on the crystallization age that we brought. So now, finally, although the age pattern from the three complexes are different, the distribution pattern of the discordant concordant data suggests Eo-Archean to Meso-Archean zircon for magmatic rocks. So our age that we believe our original crystallization of zircon, they range between 3.8 and 3.1. The homogeneous and zoned rims around magmatic cores record metamorphic ages of 2.6 to 2.0, probably formed by Neo-Archean Paleoproterozoic of high-grade metamorphism in the central zone. But we have similar ages of Neo-Archean and Paleoproterozoic concordant ages that from the magmatic zircon, which we interpret as product of resetting related to lead loss. So due to metamorphism. And the depositional age, we consider it as 3.1 to 2.7. And the paleo to Mesoarchean detrital zircon from the entire central zone were probably derived from the proximal source, that is the orthonized and granitoids of the southern part of the Zimbabwe craton, that is the Togo segment. And this 3.8 billion zircon we recorded from the Limpopo Complex, we suggested that there is a presence of the unknown older crust from the Zimbabwe craton because it has never been reported, but we see this. So it means there is a known older crust from the Zimbabwe craton. And these results also indicate that cratonization of the Azania or the Kalahari craton occurred at 2.6 billion. That is during the assembly or the collision of the Zimbabwe and Kalahari craton. And this Neo-Archean high-grade metamorphism could be related to collision of the Kalahari craton or the Diapia-driven intracratonic origin as a possible mechanism for the formation of the Limpopo Complex. So that is our systematic interpretation we used to relate to do what you have presented. Thank you very much.
Thanks for really So at the end, still was possible to tell whether the collision or diapia-driven mechanism. So you couldn't discriminate between the two hypotheses.
Yes,
we still.
Yeah, those are the two Neo-Archean models that were proposed. I think it's Van Drunen et al. And I forgot Van Drunen et al. And the other guys. So they proposed these two models in Neo-Archean. So in our case, we agree that cratonization occurred at Neo-Archean, but due to collision of the Kalahari craton and Zimbabwe craton, or it is the Diapia model, we haven't gone for that one.
Any ideas of how you might be able to do this?
Actually, from our metamorphic study that we did from the central zone, there is where we recorded ultra high temperatures in the Botswana site, which gave us temperatures greater than 900. And then we also have the high pressure, which goes up to 10 kilobar from the Garibere amphibolites in the Limpopo Complex. But if we look at the ultra high temperature, maybe there are all these ages, they are not related to Neo-Archean, they are related to the 2 billion activity. So we don't have any evidence in place from our metamorphic study that we did from the central zone that can correlate us to the Neo-Archean. All our ages, the metamorphic conditions that were recorded, ultra high, high pressure, they were recording the age of 2 billion. So they were related to 2 billion activity. But we consider that 2 billion activity as a thermal activity. I mean, intracontinental, as an overprinting, not as a collision. So therefore, we support cratonization at 2.6, 2.7.
It's really interesting work that you did. I wanted to zoom in on the source of the zircons because you said that you think the protolith was a quartzite, or it was quartzite. You think the protolith was sandstone.
Yeah.
And then you said that you feel like it's coming from the Zimbabwe side rather than the Cowfall side. But that's actually quite a significant difference because presumably those were separate cratons at the time that the sandstone was deposited. And so I wasn't sure that I understood the reason why you think their sediments are coming from the Zimbabwe side.
Usually we are getting older ages of more than 3.5 million from Zimbabwe. But in the Kapa patrol, they were not important. So, meaning that our detectors are going to contain samples which are greater than 3.5. We saw from Bruna's work, got 3.7, 0.6. We also got 3.8, 0.6. And those detectors are going to be qualities.
These have been found in the South African sites too. There's the European and Indian zircons.
Yeah, they are next week. They put about something 0.5. So then we put out the carbon and so of the and the correlation also from the diagrams, you saw from the correlation of the diagrams, they correlate very well. This is our max, our oldest age is great. And if you can see from the ortholisis and the granite veins of the top segment, they correlate very well. And remember, these are mathematics. So they should be derived from these mathematical points. And this quasite, they were just correlated because they also did some study and they believed that they also could have been derived from this ortholisis. And they correlate very well this water sediments. But this is what we believe maybe could be the source of mathematics.
Any question? I have one question. Question A, 1A and 1B.
Yeah.
First thing, this technical question. In the isotope plot, like you generally plot 206 by 235 against 207 by 206 by 238 versus 207 by 235, right? But why you plot lead uranium versus lead diagram? What is the technical advantage of this?
When we did support, we did not look at any technical advantage or disadvantage. We are not much expert on the digital diagram.
Generally, this is not a accepted or recommended diagram.
Yeah.
For isotope plot, right? You plot 208 by 206, then 207 by 205, a 235.
Yeah.
The advantage of this plot is that you can draw the discord.
Yeah, the discord, yes.
But no,
here
you can draw the discord.
Yeah.
But in this diagram, that is, if you plot 6 uranium by 7 uranium diagram, you can draw the discord. Right? You get the formation age and metamorphosis.
Yeah.
So I cannot understand the philosophy behind that, why you choose this diagram. First. Second thing, in the Kabul Keton, the Aegis ancient Nicene complex, it is a 3.6 level. So why you consider that your zircon only come from Zimbabwe?
Yeah.
There's also possibility it come from the Kabul Keton too.
Yeah, we cannot rule that, but like I was saying, we consider those because we are getting even older ages from our it has gone up to 3.7, 3.8.
Considered with that because this is not recommended isotope diagram.
Yeah.
Used in the geochronological.
Yeah, we'll also have more diagrams. I think we are another study again using the application of this method and the digital samples. So we are going to also plot the same diagrams and also plot the proposal that you are making and then make a comparison whether we wish.
My request is that please check your data with standard recommended diagram for the isotope plots.
Yeah.
And there you can draw the discordia and you can the minimum and maximum age meter.
Perfect.
Okay, thank you. Now, some photo things. This is the last talk in this forum for the year 2025. Students are happy? Very happy. On the behalf of our Geological Science Incorporated, I thank Dr. Matthew Locke, Louisiana State University, USA, Professor Andrew Green, UK resident Durban, South Africa, Dr. Helly Kauthar and Nigel Hicks from CGS Pretoria, and Dr. Thembiso O Basupi of your department to make our departmental research forum talk prestigious with their valuable and gorgeous presentation. A special thanks to Mr. Matthew Hoover for our department to arrange the online talk of Dr. Matthew O Basupi, Lottery of Louisiana State University.